Yeah, so today we are going to start a new chapter, that is the fifth chapter. So, entitled Magnetism and Matter. So, this is fifth chapter in this book. This part, uh, what we are going to learn here, we are going to learn what is Paramagnetic first, and then see, as you can see here, the title Magnetism and Magnetism and Matter. You know, uh, in the previous chapter, we had learned how electric currents or moving charges produces magnetic fields, etc. We have learned. And if you have a conductor and you excuse me. So if you have a conductor carrying a current, how magnetic field is produced by that. And even a conductor, when it is placed in a magnetic field, how is that experiencing a force? So those kind of things we have learned there. So now we'll be learning in this chapter that uh, in matter how magnetic field is created, and according to their nature, matters or materials are divided into various categories. Okay, materials, and there are in fact three types of material. Okay, one is diamagnet, then you have paramagnet. Okay, then you have ferromagnet, and we will be learning various other parameters related to this magnetism, and to compare those parameters with comparing those parameters will be able to distinguish these various materials. Okay, and we will learn here when we keep a material. Okay, we keep a material, suppose iron or anything, any like cobalt or nickel or whatever. If we keep any material inside a magnetic field, we'll see that material will allow some amount of magnetic field to penetrate into that. Okay, that is called permeability. So in fact, actually, we are all permeated by are penetrated by various type of magnetic fields, and it is said that Earth itself has certain magnetic field. Okay, so we are all inside magnetic field of some kind of sources. So this magnetism in matter was like, or I can say as a whole, magnetism was first uh, magnetism was first discovered by Greece people. Okay, so Greece people are some this. See, the first magnetic material what was discovered by Chinese people was actually magnetite. This ore of, or this is actually natural magnet. Okay, magnet was first discovered. Magnet was actually magnetite. Magnetite. Okay, so this magnetite had certain property. It was attracting nails made of iron and many other kind of metals, and it had a certain property. If you just suspend it with a string, it will be always directing north and south direction. So this is actually the first magnet which was discovered was the lodestone. It is called lodestone because with this actually they could detect the directions. And almost in BC 400 BC, Chinese people used this lodestone to get the direction, proper direction, because it is having this property to always orient in north and south direction. Okay, so the first magnet which was actually found in the nature was the lodestone, which has a name which is actually magnetite. Okay, so then thereafter, because of its various properties, we will see that. Okay, let us go to the textbook. We will first actually start this chapter with bar magnet. We'll start with bar magnet. So this introduction part you can just read for knowing the history of this magnetism. And in the very beginning itself, there are some properties of behavior known to everyone about magnetism, and those are listed over here in your book. You can see that behaves as a magnet with magnetic field pointing approximately from the geographic south to north. So this was one notion about magnetism in the very beginning stage. Then when a bar magnet is freely suspended, it points the north-south direction, and people would use this thing to get the proper direction of north and south in the earth. Actually, as I showed you, this north and south, this actually we decide, or we say, if we see this bar magnet has a north in certain direction, north pole, then we say this as geographic north pole. Geographic north pole. The geographic north pole. We'll be learning the earth magnetism here. That time we'll be explaining. I'll be explaining to you people. So this is called geographic north pole, and this is the direction in which the south pole of this bar magnet is aligning. That is called actually geographic south pole. Okay, so geographic south pole. All right, but like this, see, we'll be learning that Earth actually Earth also has magnetic field, and there are very many notions about the like reason or origin of the magnetism in Earth. People in the beginning they used to think like there is a very huge bar magnet aligned to the center or the core of the Earth, and suppose this is your south and this is your north, then this north pole of this, because bar magnet, the similar pole north or south, they repel each other, just like your repel each other, and opposite pole, north south or south north, they will be attracting each other, just like your electric charges. Same charges repel, and unlike charges and unlike charges attract each other. Similar thing here also. Not to see, if I just bring another bar magnet here, the north pole will be actually repelling each other. Okay, so it will be deflected either this way or this way, and south pole, if I bring the south pole, it will attract. Okay, so when we see that north pole, some direction, if I just held this bar magnet at anywhere in the earth, on the earth, so when you see this north pole is aligning in certain direction, that that is actually not the actual magnetic north pole of the Earth. That we decide as, that we say as geographic north pole. Why that is not uh, the magnetic north pole? Because we know the same pole will be repelling each other. So if this north pole of the bar magnet is attracting by the Earth, so in certain direction, so you must be thinking that in that direction, south pole of the Earth magnet is situated over there. So that's why this pole is called actually north seeking pole. Okay, north seeking pole, and the south pole actually is called south seeking pole. All right, the south seeking pole. So few more points we had in the beginning. Let us see. Okay, so I have told you about this repulsive and attractive forces by various poles, and we cannot isolate. So this is another important observation about bar magnet. That is, we cannot isolate north and south pole of a bar magnet. If we break it, uh, if we break it, again you will get a tiny bar magnet where both the poles will be existing. So you cannot separate this north and south pole from each other. Well, I can explain you why this happens. So that's why it is called that in magnetism there is no monopole. I'll tell you this statement. And the last statement was it is possible to make magnets out of iron and its alloys. Okay, we can, yeah, we'll be learning that part how we can make a magnet. Okay, so yeah, so practically, if you see or if you want to buy bar magnet from online or somewhere, so you look like this. The bar magnet will be looking like this practically. Okay, so this is a bar, and like north and south pole will be just either they will be putting the color or maybe they will denote north and south by N and S, kind of that. And see, you, I hope all of you have done this kind of small activities in your childhood, or maybe now also you do sometime. If you just keep some uh, filings of iron, or maybe powders of iron or any metal, okay, basically which are so-called magnetic metal. So if you just get some filings and keep on a sheet of glass or maybe sheet of wood also fine, and then place that over this bar magnet, you look how these filings will be arranged in a particular pattern. It will show a nice pattern like this. So this pattern, why we get this pattern, and or in other words, these patterns actually indicates the field lines, magnetic field lines. So these are the magnetic field lines. If you see magnetic field lines, you are familiar with electric field lines now. Electric field, as you have learned that the electric field lines, they start from positive and then end at negative charges. They will be continuous. Okay. So there is, see, here also the bar magnets. You look here, north pole and south pole. So the magnetic field line starts from or emerges from north pole and then enters into the south pole. And here the difference between electric and magnetic field, actually you look here, if these are positive and negative, so electric field starts from here, electric field line starts from here, from positive and ends at exactly at negative charge. Okay, similar in this side also, or maybe that this also like that. Okay, but they don't form a closed loop. Here actually the magnetic field line forms continuous. These are continuous field lines, continuous, and forms or magnetic field lines form a closed loop. closed loop. Magnetic field lines form a closed loop. You can see what does this mean. You look, this magnetic field lines actually penetrates the material. It goes through the material also. So it will be like this. Okay, like this. This direction will be like this. Here it will be like this. Okay. So in your book it is shown nicely. You can see that magnetic field lines are continuous and they form a closed loop. And all uh, other properties, as you have seen in case of electric field, are same here also. Like electric field lines, they don't intersect each other. There also magnetic field lines, they don't intersect each other. So you can zoom it and then see there are many field lines over here in this region, but nobody intersect other. Okay, none of this intersect the other. So what is the reason why don't these magnetic field lines intersect each other? Because if they intersect, what will happen? Suppose one of my field line is this, and another one is like this. So at this point of intersection, actually there is no definite direction. I can take a slope. Okay, so one more point I'd like to say before I explain this. So if you want to know the direction of the magnetic field at any point, okay, you have to draw a tangent at that point on the field line. So suppose here I want to know what is the magnetic field direction. I have to take a tangent over here like this. Okay, on this field line. The tangent along the direction. See, the tangent will give you the direction of magnetic field. So now here, if two lines are actually intersecting each other, then I can draw a tangent on this line. See, I can draw a tangent on this line in this direction. And for this line, I can draw a tangent like this. Okay, I can draw a tangent like this. Okay, so this tangent and this tangent are giving different direction at this point of intersection. That's why you'll not get any definite direction over there. Okay, so this is the reason magnetic field lines do not, or maybe electric field lines also, they do not intersect each other. Okay, and one more point here. Look, if I want to know what is the strength of the magnetic field, okay, at any point, and see uniform means, like I had told you that uniform field means you have to draw parallel an equidistant line, then it will be uniform magnetic field or electric field, whatever. Or in that case, any field, if you want to draw a uniform field, then you have to draw this kind of parallel equidistant line. Okay, and see, how do you understand about the strength of the magnetic field? Okay, not only magnetic field, even electric field also. If certain region, suppose I want to know what is the strength along this line, magnetic field strength. So if you just draw, see this is kind of area, and how many magnetic field lines are crossing this particular area which is perpendicular to the direction of the magnetic field. Okay, this is magnetic field direction. If you just consider a cross-sectional area which is perpendicular to the direction of the magnetic field, through this area, how many field lines are going, like passing through? If there are some 10 field lines, okay, then the strength is some strength you will feel. Suppose there is an area like this, so there are two field lines passing through that. So the strength over here is more. Here is more than here because there are two field lines which are passing through this area. So it will be less actually. Strength of the magnetic field. So it's a very simple word. The strength of the magnetic field can be determined by the density of the field lines. By the density of the field lines. So here it is shown here. You see, this is the region 1 where the strength of the magnetic field is less than this region. This is another region which is region 2. Here the magnetic field strength is more. Okay. So that's why the magnetic field strength will be here. And like at the end you can see the magnetic field lines are little bit carving because it has to come all the way here and enter here. So that's why magnetic field lines at the end are bending. Okay, so this is all. Now if okay, so yeah, you can see these things. Okay, so you can read from your book and then learn again. And see, the axis of this magnetic field is actually magnetic bar magnet. So if you just think like this is a point where the south pole is existing. This is the point where north pole is existing. This is south, and this is north. If you just add this north and south, this point, 2 points and extend, so this will be the axis of magnet. Okay, this is the axis of bar magnet, and this is the direction perpendicular to the bar magnet. Okay, okay, so this direction is perpendicular to the bar magnet, and this is on the axis of the bar magnet. Axis, it is said. And okay, yeah, I think here this is all here. Okay, so look, some people might be very much wondering how people draw magnetic field lines for this bar, for any bar magnet. Okay, it is very simple. You can by yourself you can draw the magnetic field line. Okay, by a simple experiment. Look, I'll show you the simple experiment here. You know what you have to take? You have to take a cardboard. Okay, suppose this is a black background. This is actually the cardboard, and on top of that, you can just keep a white sheet. Take a pencil. Take a simple compass needle. Okay, you have to take a compass. Okay, you have to take a compass. Now you just place your bar magnet over here. Okay, bar magnet here, and then what you have to do? You have to just place. Suppose here I can place sometime. I can place here. Then you just go away from this. You start from north or south, whatever. You can start from north. You can start from north, and like see any compass needle, it has an arrow like this and a dot like this. Okay, in the middle it will be clamped. Okay, pivoted. So this can be rotated. This can rotate with respect to like through this or about this axis, passing through this pivot. Okay, so this is actually south. This is north. This points. This arrow is actually north, and this is south. Now, if you bring near the north pole, just here, you look at the magnetic here. Actually, magnetic field line. Yeah, this compass needle will be pointing north pole in this direction. Okay. Then you just give a point. Just give a point where it's north. Where is its north pole is pointing. You take these points. Okay. As you go around, let's say, go away and away and away from from north pole, you look that this compass needle is actually orienting. You have to actually give a give a point in which direction north pole is pointing, and then give this points, mark this points with a pencil on this white tracing paper, and you can keep here also maybe. So if you keep exactly here, like you will look like this. Okay, you look like this. Okay, and if you look here exactly in the middle it will be looking like this. Okay, here like this. Okay, like this. If you do in the opposite side, you look like this. It has to go like this, so it will be like this also here. Okay, it will be looking like that. So similar experiment you can do on the opposite side also. If you now connect all these tips, okay, the points you had taken, then you will get something like this. And so arrow you have to give in the direction of the north pole of the compass needle. So this is how you can draw the magnetic field lines. I don't know whether you have already learned this thing in your previous classes, how to draw magnetic field lines for a bar magnet. If you have learned, then it is a revised session. If you have not learned clear, then you have learned it. Okay. I hope you'll. This is not included in your book, so better to know how to draw practically field lines. Okay. And now what we'll see that the bar magnet can be thought of as an equivalent solenoid. I'll tell you why. Look, we have learned how to draw the magnetic field lines for a solenoid, and now we have learned how to draw magnetic field lines for a bar magnet. So the shape of the bar magnet, you look here and look here, and also here and here. The magnetic field lines are actually having the same kind of pattern, similar type of pattern. So if this is the case, if when there is a similar pattern of this magnetic field lines, we can actually compare this bar magnet with solenoid and tell that the bar magnet can be thought of a solenoid. Can be thought of a solenoid. All right, can be thought of a solenoid. Now I will tell you how we can see. We have learned that bar magnet, a bar magnet, if we break, what happens? This is south and this is north pole. If we break in the middle, suppose, okay, then you will see there will be two magnets now. Here the south pole, here the north pole, and here it will be south and here north. Okay, you will get two bar magnets. As I said, you cannot separate north and south pole from each other. The strength of the bar magnets will be lesser. Here, say compared to this whole bar magnet, the strength will be less. Okay, less strength for both of them. Okay, strength will be less, but you will get two bar magnet. If you just break exactly in the middle, then you will get two identical bar magnet of having same strength maybe. Okay, so you might be thinking, how does it happen? So you know, if we compare a bar magnet with a solenoid, you know how solenoid creates magnetic field. Solenoid also can be thought of a combination of circular current loop, isn't it? There are many turns and turns are in the same direction. Okay, so solenoid also can be thought of many current carrying loop, combination of many current carrying loops. See, look, this one, this, then this one, then this one, like this. But in each case, if you, since the magnetic, the direction of the current of the magnetic field is same, so the magnetic field created by each of them along the direction of axis will be added up, and then you will get the magnetic field. Okay, for a solenoid. And we have learned that for any current carrying loop, the magnetic field in the like at any point on the axis we had calculated, and there we had concluded. In fact, Ampere had concluded that magnetism in matter can be explained by circulating current. Okay, circulating current. Understand? These are not touching each other. So circulating current. I'll tell you that thing, that see, any current carrying loop, it acts as a dipole. Do you remember that? It acts as dipole. Suppose the current is flowing in the anti-clockwise direction like this, then the magnetic field, okay, so magnetic field lines will be actually, see, the north pole will be created here and south pole will be created here. So if you draw the magnetic field lines will be emerging from here and entering here. So emerging from here, entering here. So we can think of that think of this thing that this loop is actually now behaving as a tiny bar magnet. Tiny bar magnet. In fact, this solenoid also is composed of such kind of turns or loops, current carrying loops, and you can think of this solenoid as a combination of small tiny magnetic dipole, okay, magnetic dipole or tiny bar magnet. So I'll just explain now, when we break a bar magnet, how do we get again a bar magnet, and how we are not able to separate this north pole and south pole from each other. Because if I just consider this bar magnet as a solenoid, it has small current look like that, okay, like this, all right. Or I can think of small tiny bar magnet also, tiny bar magnets also. So these loops are actually acting as tiny bar magnet. Yeah. Now see, the current is actually flowing in the same direction for all the loops in this solenoid. If I say the current is flowing in this direction, so in this direction, then look all the way, it will be like this, and for this loop it will be like this and here, okay, and then like this. I will just draw all of them, then I'll tell you what I'm going to say. Like this, and you can draw like this. Okay, look, if I just take all the things, see here the south and here suppose north, again here south north. So you look nearby, any nearby loops, two loops, suppose here is south and here is north, again here is south and north, because the current flowing in each loop in the same direction. So here it is north again. So this north and south, they will be cancelling each other, they will cancelling the effect of each other. So you will ultimately get a bar magnet where you have a south pole here and north pole here, and in between there is no magnetism here in between. So that's why this point, middle point or a region will be there, that is called actually neutral point. Okay, this point is called neutral point. Neutral because there is no magnetic field or no attraction, nothing you will feel here in the middle. You will feel at the edge, and obviously edge means not exactly at the edge here, it is just before the edge. Okay, your north and south pole is situated, kind of this. Okay, now let us see, if we break, what will happen. So in general, what they do, they cancel this, say nearby north and south pole effect, they will cancel each other's effect. But if I break over here, look here what happens. See, this part will anyway, this will cancel, this will cancel, this will cancel, but this side again south, and see this part is not cancelled by any other. Okay, then it will retain its north pole nature. Okay, similarly here, these two will cancel, these two will cancel, again these two will cancel. So here it will be south and here it will be north, retaining the same thing. Okay, so this is how bar magnet, if you break again and again and again, you'll find out the tiny piece also will act as a bar magnet having south and north pole. Okay, all the way. Okay, in fact, you cannot break or separate S and N from each other. That's why it is said that in magnetism, monopole does not exist. Does not exist. What does this mean? Does not exist. Okay. So what does this mean? This means that pole means what? This is either north or south. Each of them are called pole. And monopole means any one of the poles. Okay, any one of the poles is called monopole. Like in case of electric charges, you can find out either positive or negative separately, and also you get a dipole where electric positive and negative charges are separated by certain distance. But in this case, you always see your north pole and south pole separated by certain distance, and this is the fundamental unit for magnetism. Okay, so fundamental unit for magnetism is magnetic dipole or current carrying loop. Fundamental origin, I should say, or origin of magnetism is a magnetic dipole. So magnetic dipole or a current carrying loop. Carrying loop. Okay, so this is the thing. Now, see, there are certain differences also between this bar magnet. This is bar magnet, and this is solenoid. There are certain differences also. This is actually naturally obtained, and it does not depend on external field, etc. And this we can make a loop and then pass the current through that, and we can create magnetic field. So this is not natural. This is not natural. This is man-made. Okay, this is natural. Bar magnet is actually natural. And the strength, as I said, it does not. The strength of the magnetic field does not vary for a bar magnet, but for a solenoid it varies, and it can be controlled by external current what you send through the coil. Okay, so these are few things. Okay, about bar magnet and solenoid, like distinguishes between them. But anyway, the field patterns, magnetic field patterns are same. That's why you can compare a bar magnet with a solenoid, and you can say that bar magnet is an equivalent solenoid. Well, see, in this place, uh, then suppose you want to confirm this, confirm or affirm. Hello, Priyadarshini, are you getting sound? Are you able to hear? Actually, Guna madam is saying that you people are not able to hear. Are you people hearing or able to hear something? Can you message me? Please message me so that I can understand whether you are able to hear or not. Hello, are you able to hear now? Guna madam, are you able to hear? Are you people able to hear me? What about others? Students, are you people able to hear me? Please message me so that I can resume the class, whether you are able to hear or not. Am I audible to all of you? Hello.
Sir,
If people can message me. Yeah, madam, I can see your message, but I don't know whether others are hearing. They are not replying. I don't know. Maybe they are not able to hear.
sir,
Deepa,
yes,
Deepa,
sir.
You are saying
Yes,
something, but I'm not able to hear you. Can you message me? Can you write in the message box? Can you write in the chat box?
sir.
Samita, Priyadarshini. Hello. Are you people able to hear me? I think I don't know what is happening. Hello. Okay, I don't know. It is difficult to actually continue with this without your response because I don't know whether you people are able to hear me or not. Good madam, can you reply me whether you are able to hear now?
Sir,
Okay, nice.
hello,
So
sir.
Deepa, you
Yes, sir.
are saying
Yes, sir.
okay. Yeah, Deepa, can you message whether you are able to hear? No, Deepa, actually your voice is not coming. I am not able to hear your voice.
Sir,
You have to message.
one minute, sir. I sent.
I hope you are able to hear. What about Priyadarshini and Samita? Samita has left now.
I sent a message. Send the message, sir.
Okay, Deepa is saying that she can hear.
Yes, sir.
So, Guna madam, shall I continue or shall I stop it here today? And then I'll rectify the things in the next class. What should I do?
Okay.
Shall I continue with this? Actually, I'm not able to hear back you people. Shall I continue?
Yes, sir.
Priyadarshini, shall I continue? Are you hearing me? Samita, are you hearing me? Can I continue? Write in the chat box. Okay, so you people are saying that you people are hearing me. So I'll continue. I'll continue with this another maybe 15 minutes. Okay, because we have lost few minutes. Okay, I'll just finish this part what I have started here, and then I'll stop. Okay. So if anything, like if people are not able to hear and all, you just message me. I can see your message, but I cannot hear you back. There is some problem, technical problem.
Okay.
Okay. So look, to confirm whether a bar magnet can be uh, thought of as an equivalent solenoid, what we are doing, we are taking a solenoid of length 2L. Okay, and then what we'll do, we'll calculate the magnetic field on any point in the axis. This is the axis of solenoid. Okay, we'll calculate magnetic field due to this solenoid. See, this is a solenoid. As consider that there are n number of turns. Okay, n number of turns per length, like per unit length. So this is a solenoid. So this is a solenoid I have taken. What are the things here? Suppose the length is 2L, as you can see. The number of turns per unit length, number of turns per unit length is small n here. It has, as you can see, it has a radius. The radius of the solenoid is A. Okay, and I am calculating magnetic field on the axis of this solenoid at a distance r. Okay, from the center. See, I have just thought that this is the center of the solenoid, and from here I have taken a point P. From that point, the distance is r, which is shown over here. You can see in your figure from the textbook. So, if I just put my origin over here, then I can calculate the distance from here. So I can say this is plus L, and this side up to this it's minus L. Okay, distance from the origin left side it is minus L. Okay. Now from this origin, this point P where I am calculating the magnetic field for this solenoid, the distance is R. Okay, R from the origin to this P. All right. So what I'm doing actually, see, I'll be applying my knowledge, what I know about magnetic field created by a current carrying loop, because a solenoid is composed of many turns. Okay, many loops. So I just I'll be applying my knowledge. You know, you might be remembering the magnetic field expression for the magnetic field for this kind of loop. You know, the magnetic field will be in this direction, and see, this was mu naught n. If there are, so if this is only one turn, I can take I mu naught the current through the wire I, then it is actually 2, and into here it was a square. Here the radius of r, so it was okay. I can write just r square divided by this. This is the distance from O to P. So this is x plus this is the r again. So x square plus r square multiplied by 3 by 2. So this was the expression for the magnetic field. Okay, created by a single loop at any point on its axis. So that point is actually from the center at x distance away. So if we write, see, I just consider similar thing here. I'll consider similar thing here. I think uh, it, it a ring, okay, a ring of thickness dx at a distance x from the center. You look from center, this is at x distance, where I'm calculating kind of ring. I'm just thinking of a ring of uh, distance or length dx. Okay, thickness dx. So how many number of turns are there? If I know number of turns per unit length is this, so in this dx, how many number of turns will be there? N into dx. So this is my n into dx. Okay, this is the number of turns. So if in each turn there is a current I, so what will be the total current in this dx thickness? So this much will be the current n dx. So this is the total number of turns in this particular ring. Okay, there are n dx turns, and in each, if the current I is flowing, so total current will be n into I. Okay, so if I write this same expression for this particular solenoid, and suppose we are calculating the magnetic field from this O2, like magnetic field on any point on the axis, that is P, and which is from r distance away from the center. So look what I can write here. The magnetic field I can write for this is actually, suppose dB, because I have taken thickness dx. Okay, dB for dx thickness element. Okay, element kind of a ring. Okay, so the magnetic field, so mu naught will be as it is by 2 as it is. Now I, what is the I here? N dx, this many number of turns into I. This is the total current. And what is the r square here? The radius of this solenoid is a, so a square over here. And now look, so this distance I have to see. I have to write a square. This is the c r square plus the distance x. The distance is x was actually from the center. Okay, because your loop was at that place. Okay, now my loop is here. Look, this is my loop now. This is my loop. So this is the center over here now for this particular loop. Okay, so this center is already, see if I just calculate the distance from O, so this is actually x, this is x, and I am calculating the magnetic field for this particular loop, okay, of thickness dx. So I have to calculate, I have to take the distance, effective distance from here to here. Okay, instead of writing x, I have to write, so this is total r and this much is x, so I have to write r minus x whole square. Okay, and whole to the power 3 by 2. I hope you guys understand this. Okay, all right. So this is the thing. So this is the magnetic field due to this particular element. So if I want to calculate the magnetic field for the whole solenoid, so what you have to do, you have to integrate it. So how do you take the limit here? Because you have half part this side, okay, half this side and half this side from the origin. So you have to take the limit minus L2 plus L over here, okay, over the distance. Okay, this. So this dx you have to integrate over dx, and the limit you have to take minus L2 plus L. Okay, if you integrate it, you'll get the total magnetic field at this particular point P due to this whole solid. Okay, so this is the integrable thing, and this dx is the parameter with respect to which you have to integrate. But in this case, you know, like you don't have to do the integration part. We'll just do certain approximation. You know, we are physics people always go for approximation rather than handling too much complicated mathematical formulation and etc. We'll just, and also sometimes if you don't take approximation, things will not come as your real thing. Okay, so that's why that is the difference between mathematics and physics. Mathematics go with their calculation rigorously, but we go with the reality. So now, suppose in this case, my r, the distance where I am calculating the magnetic field on the axis is much greater than the radius of the solenoid as well as the length itself. Okay, length itself much greater than L. So then I can do certain approximation to this denominator. Okay, so see what approximation I can do from here. R minus x whole square whole to the power 3 by 2. This I can see, since A is much greater, R is much greater than A. So R square, if A square is obviously less than R square. So it will actually, approximately, and also X will be much less than the R. So approximately I can neglect this part, this A square, and as well as this X. So I'll get R square whole to the power 3 by 2. So finally you'll get approximately R cube. Okay. So I'll write this approximation. If I apply this approximation to here, look what I can write. The expression for this magnetic field. So B means there is integration. So inside the integration, I'll keep only the. So this is 2. This is n dx. Okay. So dx I'm not writing here. N into I, and divided by c. This is whole thing is actually r cube. And here integration minus L2 plus L dx. Okay, dx. So if you integrate it, this will give dx over dx. If you integrate it, you will get the length of the solenoid itself. This is dx, integration over dx in the limit minus L to plus L. So this will give you 2L. This part will give you 2L. So if I write that, the magnetic field at this P point for whole the solenoid will be mu naught I n I, and then this is 2L. Okay. Okay, I have forgotten this. I have actually not written here this a square. So a square also will be there in the numerator. A square is there, and in the denominator it is 2 r cube, simply this one. Okay. Now look, if I simplify little bit to make it familiar to one of our known term for electric case. See, what I'll do, I'll write mu naught by 2 r cube here. Okay, so look what I'll write here. This 2n into n, this is the total number of turns. This is I. Okay, and see, if I just multiply pi over here, so this pi is square. So this will give you the area of this solenoid. Okay, so pi in the denominator also I have to write. So look, this one 2ln, this is the total number of turns. This is I, this is the current, and this is the area. So what is this? Area is pi square. Okay, pi square. This is the area I am writing. So this part is actually nothing but your magnetic moment M. If you write this area vector, so you can write this as magnetic moment vector. So I'll write that. Okay. So if I write B vector, look here, it will be mu naught by 2 pi r cube into here M. This is whole thing is M vector. Okay. This I get. This is what I'll get. Okay. So now if I multiply again 2 both in the numerator and denominator, what I'll get is mu naught by 4 pi into M vector by 2m vector by r cube. So this is the similar thing you might have okay, you might be remembering, you have already learned it in the electric case also. When you calculate a magnetic field for an electric dipole. Okay, electric dipole, you see at any point on the axis what you get electric field, you get 1 by 4 pi epsilon naught, this thing, and 2p, this is vector 2p, this is the electric dipole moment by r cube. So this is what you have got. So look, this I can compare. So electric and magnetic dipole. So this I can show you this the similarity in case of electric and magnetic field also. Okay. So if I so you can see that this solenoid actually acting as a magnetic dipole, whole and a big magnetic dipole, or I can say this is acting as a bar magnet. Okay. In fact, if you take a bar magnet and calculate magnetic field at the same distance from the center of the bar magnet, experimentally it is found that the magnetic field is found to be this one. Magnitude of the magnetic field is found to be like this. Okay. So yeah. So this is what confirms that you can think this solenoid as a bar magnet. Okay. So this is what you can see. Even if we calculate, if we calculate the magnetic field at any point on the equatorial plane also, as we have seen in case of electric dipole. So comparing this electric dipole, we can write the magnetic field which is at the equatorial point anywhere over here. You can write this as again mu0 by 4 pi m by r cube. Okay, here it will be exactly half, and obviously there will be a sign difference will be there. There will be minus. So what you have already learned in case of electric dipole. So we can compare electric field or electric dipole and magnetic dipole, or in other words, I can say bar magnet and solenoid. They are equivalent to each other. Okay. Okay. So in the next class, we will take up the next topics. Okay. So because of this sound issue, uh, I could not finish this bar magnet. A little more is remaining, but already we are like out of time. So next day I'll just finish the little portion which is remaining for the bar magnet, and I'll take up the next portions. Okay, we'll again meet on this Wednesday, and I'm just trying to rectify this sound issue. Without your response, sometimes it is very difficult to teach. Okay, so all right, then see you on Wednesday. Okay, bye. I'll stop it here. Yeah, bye for today.